GM, and welcome to a walkthrough of World ID services, how they work, how different infrastructure repos connect to each other, and just like overall walkthrough of every single component that you need in order to have a functioning World ID protocol. So everything from the WorldCoin perspective always starts with the user, right? So the user, when they first think of WorldCoin and they want to create a proof of personhood, or in order to have a World ID, they first need to go to an orb. They need to download the World app, as we can see over here. And once they have the World app, they go to an orb in person and they register, right? They just show a QR code, they stand there for a minute, they get the World ID, and once they have the World ID, they're able to create proofs of personhood. All right, so that's like a high-level conceptualization of how it works, but there's a lot of things you can see that are required in the technical point of view, from a technical standpoint, for everything to work. So once we have the user, right, the user will go to an orb, it will generate a valid iris code for that specific user. And once that iris code is deemed to be unique, by the way, this is the WorldCoin white paper documentation. So if you want to see how the proof of personhood part from the orb works more specifically, you can scroll down over here and you can see like all the math for like how do you determine that a person is unique. And this is the thing that I called to be an iris code, dimension to be an iris code. So if this iris code is unique, meaning that the distance between different iris codes, you can think of them as vectors. If the distance between them, Hamming distance between them, is sufficiently large enough, they're deemed to be unique, right? So for a match, this is the distribution for a match, this is the distribution for a non-match. So if you match, then a public key that was generated by the user, we call it an identity commitment. So on the app, you generate a private public key pair, and the public key for that specific user, if the iris code is unique, one of the left ones, one of the right ones. Okay, that's my bad. So this is matches and non-matches, meaning that if you match, the person is already registered. If it's a non-match, it means that they have not registered before, right? So if you have a unique iris code, that's my bad. If you have a unique iris code on the right, it means it's a non-match. Then the public key for the given user gets inserted into the set of verified users. But how is the set actually implemented for that specific user, for our user base? So if we go to the architectural overview, right, we see that once we go through this uniqueness check where we verify that the iris code is unique, right? We verify that the distribution is a non-match distribution. We go to the identity sequencer, or a World ID indexer and sequencer, which takes the public key from the verified user and inserts it into our on-chain smart contracts. So the way that this sequencer works is that it has essentially an API route that allows you to post a given identity commitment. And in the identity commitment, which is the public key of the user, it batches a group of identity commitments. And once it has a specific group, we are currently running on batches of 1,000 identity commitments, or 1 hour, whatever comes first. So we insert users every 1 hour, or if 1,000 users are in a batch. So once you generate this batch, you essentially update the Merkle tree root in a batch. So like, again, what is a Merkle tree? A Merkle tree is a data structure. I can just pull up an image, Merkle tree. So a Merkle tree, you can see is like this little data structure. So a Merkle tree essentially has some leaves. These would be the identity commitments. And once you have the identity commitments, what you do is you essentially hash each individual pair to generate like a subpair, and you essentially hash these pairs of hashes until you get a root. And this would be the data structure of a Merkle tree. And why are Merkle trees useful or used within World ID? Well, it's to prove inclusion, essentially. In order to prove that you have a specific leaf in a data set, or in the set of verified users, you can essentially prove that I own a public key, which is in the set of verified users. The way that you do that is you provide a thing called the Merkle path. You essentially provide all the siblings to that specific path in order to prove it, right? So for example, if you want to prove that you own L1, well, you'd provide a Merkle path for hash 01, hash 0, then hash 00, sorry, hash 00, hash 01, hash 0, and hash 1. With all those siblings, you'll be able to essentially prove inclusion of L1 because you'd be able to reconstruct the root of the Merkle tree. So that's a Merkle proof. And the cool thing about world ID, if we go back to our documentation, the cool part about world ID is that you can prove inclusion without revealing which leaf you are. And that's done using a protocol called semaphore. So if we go and just search for semaphore real quick, semaphore ZKP, there's this protocol built by a privacy key explorations group from the Ethereum Foundation, which essentially allows you to prove that you own a private key to a public key, which is in a Merkle tree of users of any form. So this is what it's called, a semaphore identity. We call it a world ID, pretty much, in the sense that the public key that's in the set of registered users can only be inserted if the person is unique. So that's like the additional logic on top of a just vanilla semaphore group. So once we have that, we can go back to the diagram. We can go right here. And we can see that once we have the world ID sequencer, right, we're going to be doing like updates of this semaphore tree or of this world ID Merkle tree in batches. The reason why we do it in batches is because if you do like one smart contract transaction every single identity for every single user, it would be very expensive, get very expensive very quickly. And since if you have a batch, you can compute this batch off-chain and just insert the batch at once. So actually, we can go a little bit over the structure. So before we insert a given identity, when we're generating batches, the way that we generate these batches is through a zero-knowledge proof as well. We have this repo called semaphore MTB. So semaphore MTB stands for Semaphore Merkle Tree Batcher, and it's a set of zero-knowledge circuits written in Gnark, which is a Go Snark framework written by consensus. And these circuits essentially compute the Merkle tree updates off-chain that we do, these batch insertions and batch deletions. So for example, here we have an insertion circuit where we can insert different batches, right? We have some identity commitments, some previous root, some post root, and at the index that we start to insert for, and the batch size and the tree depth. So this is the batch size, right? So currently this would be 1,000 in production, where we're inserting batches of 1,000. And we recompute the new Merkle tree root, and we provide a proof to the contracts to update the latest root. So now if we go to world ID contracts, which is another repo, right? So this is all public as github.com/worldcoin/world ID contracts. If we go to the implementation, we can see that there's a register identities function. And here we take an insertion proof. So this insertion proof is generated under the hood by semaphore MTB and essentially proves that this new Merkle tree root with new insertions has been correct. So yeah. So once we essentially the sequencer batches all of them, all the new identity commitments, it creates a proof and it sends a call to the smart contracts. So what is this sequencer thing exactly? So we can take a look as well. So it's a repo called Signup sequencer, also public. So if essentially it's you can think of it as a server that you can post requests to, and it handles all the different logic. So if we go to the server file, we can see that there's essentially a list of API routes that we have. So one of them is insert identity, the other one is delete identity. For example, we can add a batch size, remove batch size. This is like all utility API routes. So the ones that we're most interested in is, for one, verify semaphore proof, inclusion proof, insert identity, and delete identity. So insert identity is what we've been talking all along, where we can post a given identity commitment to this API route, and the Signup sequencer will batch the set of identity commitments until it hits its threshold. In this case, it's 1,000, and then it will handle all insertion logic for the chain. We can go into code if you're interested later, but this is essentially like the Merkle tree that we have. There is a Merkle tree data structure where you can version trees based on if they're canonicalized, like finalized on the chain. But essentially there's a tree of hashes. They use the Poseidon hash function because we need to compute them inside of a zero knowledge circuit. And the Poseidon hash function is friendlier for zero knowledge circuits as opposed to something like Ketchak, which we're used to from Ethereum, for example. So yeah, this is like the gist of what the Signup sequencer is. It is a service that gets requests to insert identities that are signed by orbs. And these identity commitments are just public keys that were generated by users that have been verified at an orb. So yeah. The World ID contracts, which is the second part, as I mentioned before, has a register identities method that just takes in an insertion proof from semaphore MTB and updates the roots. And once we update the root is the only information that needs to be public within World ID to be able to prove that you are a unique user. The way that works is, as I mentioned before, the semaphore protocol. The semaphore protocol allows you to essentially create a zero knowledge inclusion proof for a given identity commitment. So if you are a user that went to an orb and you have a World ID, what having a World ID means is that you have a private public key pair, and the public key is inserted in the set of verified users. And so using your private key and a Merkle path, which is served by the inclusion, it's served by the signup sequencer. So if you have a Merkle path to your specific identity commitment in the entire Merkle tree, and the private key to a given public key which is in the set, you can create a semaphore proof. How do we create this semaphore proof? For semaphore itself, there is a library called zkKit. I presume it's this one. Yes. So this is the library that semaphore uses, like from the private key inspirations group. But we created bindings in Rust, which are called semaphore.rs. So semaphore.rs is a library that allows you to create zero knowledge proofs. In this case, we're using, or semaphore uses Gross16 proofs, R1CS arithmetization and Gross16 backend. So essentially, there are circuits that were originally written in Circom by PSE, and you can create zero knowledge proofs of inclusion using semaphore.rs, which is bindings for semaphore written in Rust. So yeah, here is like a sample demo of how this would look like. So these identity commitments we already have. We get a tree depth, and then we get a given leaf that we want to create an inclusion proof for. We create a tree. In this case, this is the tree in the signup sequencer. We fetch a Merkle proof, and once we have the Merkle proof, we can create a zero knowledge proof from all of these things, right? So if we have the Merkle proof and a given identity commitment, we can create a semaphore proof. Semaphore is a little bit more sophisticated than just creating a zero knowledge inclusion proof, because semaphore also allows you to prove that a given leaf did not do the same action more than once. Because semaphore was essentially created as a privacy voting mechanism and privacy like messaging as well, if you want, privacy preserving messaging or Sybil resistant messaging. Essentially, there's this concept of a nullifier hash. A nullifier hash is, as you can see here, it's the hash of a signal and the hash of an external nullifier. In this case, it's an app ID. And what this means is that if you have an action that you want to do only once, let's say that we have a voting mechanism, for example, a DAO that wants to vote on some proposal. So this proposal, you can gatekeep it for a given semaphore group. So only members of a semaphore group can vote on this given proposal. And the way that it works is that you represent the proposal with a given app ID and a signal, which can be like a given semaphore group. And so once you have these two things, you can take them together, hash them, and you have this thing called an external nullifier hash. And this external nullifier hash is what you can use to essentially make sure that a given action was only done once by a given member of the semaphore group. So within world ID, for example, as you can see here, within world ID, whenever you're doing a world ID proof, let's say that you want to prove that you're a unique person in order to claim our biweekly grant. Well, the way it works is that we have an app ID for each given grant for every 2 weeks. And if you prove that you are a unique user and that your nullifier hash has not yet been consumed, meaning that it's not been yet used to claim a grant before for that specific period, well, then you can claim the grant. Otherwise, it will just revert. So this is sort of like a general high level point of view of how everything works from a bird's eye view. There are some other components we can also talk about, but this is the generic understanding of how World ID works. So just to recapitulate what we have so far, we have a Merkle tree of identity commitments. Each of them are unique. Each of them are essentially verified by an orb to be unique. The orb proves two things: one, that a person in front of it is real, and second, that the person is unique. They've not been before an orb before. They're not in the set of verified users yet. So if you meet those two things, you can generate a public-private key pair on your phone, and you can insert your public key into a set of verified users. And using your private key, you can prove that you're part of the set without revealing which specific public key you have. That's the privacy preserving nature of World ID. And we use semaphore to prove inclusion inside of a group without revealing which specific member of the group you are. And with this concept of nullifiers, you can essentially prove that a given user has not done an action before. If you want to learn more about nullifiers and how to use those within an application, we also have the World ID documentation. So if you go to docs.worldcoin.org, here you have a bunch of the ways that you can use World ID for. So there's signing with WorldCoin. This is like a traditional Web2 authentication service, whether it's like Auth0 or Next.js Auth or NextAuth. So you can use that as a Web2 traditional OAuth provider, or you can use anonymous actions, which is the on-chain part of things, where you can gatekeep a on-chain action on, let's say, Ethereum or Optimism by having to verify a World ID proof on-chain first before you do the action. So let's say if you have a DAO proposal where you can gatekeep a DAO proposal on-chain by requiring a World ID proof, and this World ID proof will be essentially gatekeeping users to only have to only be able to vote if they're a unique user and if they've not voted for the proposal before. So if you want to read more, I strongly recommend docs.worldcoin.org. So, right. So this is like the generic overview. Now that we have that, we can dive a little bit deeper into the different technical components of World ID. So I mentioned before that we have a Signup sequencer. The Signup sequencer is this thing that essentially monitors the chain and monitors the incoming requests to insert new identities or identity commitments, public keys of users that have been verified, into the set of verified users. So as I mentioned in the server, you have different endpoints that you can call, and these endpoints are called by our orb backend to essentially insert identities as they're verified by an orb. And there are some public endpoints like the inclusion proof endpoint, which can be called by anyone. For example, the app backend, like within the app, if you want to verify when a user is claiming a grant, if you want to verify that they're unique, well, you have to first serve an inclusion proof from the Merkle tree, which is in memory in the Signup sequencer. You serve that inclusion proof for that given identity. And once you have that identity, inclusion proof or Merkle proof, you can create the ZK inclusion proof, the semaphore proof. So once we have the semaphore proof, you can verify on-chain that, okay, now you can claim this grant. So we have also grants contracts, if you want to take a look at those. Let me just find them. Grants, contracts, World ID grants contracts. Right, they're also public. So the way that a grant looks like is, let me see, for example, the monthly grant. So the way that it works, okay, this is not the one I was looking for. I'm just looking for, I guess, the interface, or let me see the one that I'm looking for. Recurring grant drop. Okay, this is the one I was looking for. So there is a claim function in a given grant contract. So this is like anyone that might want to integrate World ID into their application. This is like a demo integration. This is just like our own integration of World ID within our own use case, which is the grants of WorldCoin tokens. So here you essentially have the claim function, which allows you to essentially prove that a user has not yet claimed a given airdrop or a given grant. So the way that that works is that you submit a proof, a semaphore proof. This is just 8 numbers in a Gross16 proof. I can go into the details of the ZK part in a second. A nullifier hash, the root of the Merkle tree, the receiver, and the grant ID. So the grant ID is different for every single like biweekly period. The receiver is the address that wants to claim the given grant, the root of the Merkle tree, the nullifier hash, and the proof. So there's this function called checkClaim, which takes all those parameters. And what it does is it first checks whether the nullifier hash is in the mapping of already seen nullifier hashes by the contract. So nullifier hashes, we can see that it's a mapping of uint256 to booleans. And what it means is if a nullifier hash has been seen by the contract, it sets that specific nullifier hash to true, meaning that it cannot be used again. This is the Sybil resistance aspect of things, where you have to keep a mapping of actions that have been done, and if the action has been set to true, then you cannot do the same action anymore. So this is the first check, right? We check that the nullifier hash is not been done before. If it's not been done before, then continue, otherwise you revert with an invalid nullifier. So if the receiver is a 0 address, we also don't want to just burn funds, therefore we just revert. And then we check if the grant is valid. This is just some logic to check whether a given grant ID is still within the 2-week period for that specific grant ID. Otherwise, you cannot claim once that period is expired. And here, this is the interesting part where we call the World ID router to verify a given proof. So this essentially calls the World ID contracts I showed earlier. So the World ID contracts, and in the World ID contracts at the very end, there's a verify proof method, which takes in a root, a signal hash, a nullifier hash, external nullifier hash, and a proof. And it calls the semaphore verifiers verify proof method with all these parameters. The semaphore verifier is just a Gross16 verifier, and these are its public inputs and the proof. So yeah, like if you verify the proof, the zero knowledge proof, then you can allow the person to claim the grant, right? If this verifies, then this function jumps back here in the stack, jumps over here, and you can set the nullifier hash to true, meaning that the action has already been done, and you call an ERC20 transfer function from the holder, which is the grant contract in this case, to the receiver, which is the user that is claiming the grant, and the amount for that specific grant for a given token. In this case is WLD tokens on Optimism. We also emit an event. This is for monitoring reasons, right? So we can like see how many grants people have claimed. You can create like Dune analytics dashboards for this as well. Yep, so this is an example of a World ID integration. This is how you can use World ID, for example. I give an example of how you can use World ID to gatekeep actions on-chain. Cool. So now that we have that out of the way, we can maybe talk a little bit more about the World ID's on-chain infrastructure and why we chose the things that we chose. So World ID, the main contracts currently live on Ethereum mainnet. By main contracts, I mean these World ID contracts. So these are the contracts where we update the Merkle tree root. Every single new user that gets sort of registered, you go to the signup sequencer. The signup sequencer batches those identity commitments and does a batch insertion. Once you have this batch insertion, you update the latest root of the Merkle tree. So if we go back to register identities, let me just find the function really quickly. Register identities. There we go. And we check first that the previous root is not the latest root. Otherwise, we revert. We can only update if the previous root was the latest root. Otherwise, the Merkle tree cannot be updated. You need to have sequential updates. We calculate the input hash. This is like the public input to the circuit of the proof. We make sure that this is a reduced element. This just means that when you have a zero-knowledge proof, zero-knowledge proofs can only operate on top of these mathematical constructs called field elements, which are numbers modulo a big prime number, meaning that all of the numbers that a field can support can be within 0 and the prime number that you support for that specific field. So this just makes sure that the given hash that you create, which is in this case a Ketchak hash, because that's the Ketchak, and the Ketchak is the only hash function that's supported as a precompile within Ethereum, at least the most used one, if I'm not mistaken. And you essentially make sure that this hash is within the field, so you can operate on it within the zero-knowledge circuit. So once we do this, we route for a given batch insertion verifier. So each batch requires a different circuit, each different batch size, right? When you have a Merkle tree, we have a Merkle tree of tree depth 30, meaning that it supports up to 2 to the power of 30 identity commitments, which is about a billion, a little bit over a billion. So currently, we can insert up to 1 billion users if we want to. At least we support the contracts to support up until that. Otherwise, we'd have to upgrade the contracts and migrate every single identity commitment to a new tree. So this is the reason why it's so big. We don't want to do those upgrades anytime soon. And so for each different batch insertion, each different batch size, if you have a batch size of, let's say, 10, of, let's say, 100 or 1,000, that batch size and that batch insertion operation is different. It's you have to resize the circuit in order to have more constraints to constrain every single identity commitment to construct a Merkle tree root, right? It's a different computation in the sense that you're having more things to prove, therefore you need a bigger circuit to constrain every single computation in between. So here you just have a mapping of batch insertion verifiers, a mapping of UN256 to a verifier. And if you essentially check this array of batch insertion verifiers, you route for a given length. So you're essentially checking how many identity commitments you're inserting into the world ID tree. And then once you check how many there are, you can route for a given batch insertion verifier. And then you can verify the proof of insertion. So we not only generate proofs of inclusion, but whenever we're changing the Merkle tree on chain, we need to prove that we've inserted a given set of identities and that the new Merkle tree root matches to the insertion of those new identity commitments into the tree. So once we route for the correct verifier, here we just verify the proof. And if the proof goes through, we update the latest root to the post root, which was posted as a public input to the function. And we also put the previous root that we had into the root history and attach a block timestamp. This just means that we have a validity of previous roots. So if you want to create an inclusion proof against an older root because you may not have seen the latest state being updated, well, those roots are still valid. So the proofs won't error out. That's why we do that. And we also emit an event on tree changed from a previous root to a post root, and the operation that the tree changed, the operation that we did to change the tree was an insertion. This is all that is. Otherwise, you just revert with an error string. Or you revert with a proof validation failure if the proof was not correct. So this is essentially how to register new identity commitments into the Merkle tree. Another fun thing to note is that we post every single public key or identity commitment as call data. So this is essentially for decentralization reasons. If anybody wants to sync the current Merkle tree of world ID users or world ID public keys of users that have been verified at an orb, well, they can do so from Onchain data. We're currently working on a world tree service, which essentially would allow anybody to run this service. It's currently not open source, but it's going to be really, really soon. We just need to finish a bunch of tests. And this would allow everybody to essentially sync the Merkle tree root from on-chain call data. It's a Rust service that just parses every single event for this tree changed event and inserts like identity commitments into a Merkle tree and computes the latest root from Onchain call data, and also allows you to serve inclusion proofs against those roots. We call it a tree availability service internally. So that's that. We're also recently allowed the feature of deletions. Maybe I can talk a little bit about that. So deletions is part of a new set of features which allow you to essentially recover your world ID or reset your world ID. The way that that works is that if a given user loses access to their private key for their world ID, let's say that they lose their phone or they just remove it, delete the app, and don't have a way of recovering it, well, then they can go to an orb again. The orb will compute the same iris code for the same person. It will go to the mapping of iris codes to public keys, and it will delete that specific public key from the tree. And once it's deleted, you can insert a new one. Also, if somebody just wants to request their public key being deleted from the tree, they can do that as well. Right. So this would essentially allow anyone to delete a public key from the tree, their own public key from the tree. And if they delete it, then they can insert a new one and essentially reset their world ID, because they now have a new public key, which is in the set of verified users. And they can create inclusion proofs against it. So this is the similar logic as with insertion, but with deletion. And on the prover side, there is a circuit for deletion as well, which is very similar to the circuit. So this is, as I mentioned before, is Gnark, the Ghost Gnark library built by Consensus. And what this does is it essentially checks that you have some root with some previous identity commitments that you had, and that the after this computation, what you have is a zero identity commitments. You're essentially like deleting from the tree. And this is what the circuit verifies and creates a proof for as well, right? And the on-chain contracts, on the other end, are the ones who, let me find it right here. The on-chain contracts are the ones who verify this deletion proof and update the previous root to the next root, which already has those identity commitments deleted from the tree. You might ask yourself, why not just keep the Merkle tree on-chain? And that's for cost reasons. It's very infeasible to do Merkle tree operations on the chain, and that's why you do them off-chain. If you have a Merkle tree of tree depth 30, well, that's 30 times UN256 for a given identity commitment. So you can think of it as like 1 billion times 256 bits, which is a lot of data, and it's infeasible to do a single operation on this tree within a computational environment such as the EVM, which is very computationally constrained because there is a block gas limit of 30 million gas per block under EIP 1559. So that's sort of like the reason why we're doing off-chain Merkle tree operations, and we just prove those operations to a Merkle tree on-chain. You're just doing off-chain compute, which is cheap. You prove the compute to the chain. This is like a very popular paradigm that you've also may have seen with things like ZK coprocessors recently. So yeah, this is a part of of how the World ID contracts work. And another worth thing to mention is that World ID has been built in a way where anybody can sync the tree, anybody can create inclusion proofs against the tree, and anybody can also bridge the state of the tree to any network they want in order to support World ID on their own network. So this ties into the concept of state bridges. So state bridges, if we go to the World ID state bridge repo, state bridges are just services or contracts that bridge state to a given network. So here we have a simple diagram that I made in XCollyDraw. So essentially we have the World ID Identity Manager. This is the main contract that I showed you before for World ID contracts. And we have different bridges that you can essentially use to propagate the root of the tree to a given chain that you want. So if we check out the World ID contracts for the state bridge, for example, the most used one is the optimism bridge, because our app supports optimism, right? So when you get a world app, we deploy a safe multisig for every single user. And that user can claim grants on Optimism by verifying their uniqueness. This is how users claim WLD tokens every 2 weeks. So in order to create and verify World ID proofs on Optimism, we need to bridge the Merkle tree root. The Merkle tree root is the single public input that you need in order to verify the zero knowledge proof of inclusion. Because when you're creating a zero knowledge proof of inclusion, you need to prove that you have a Merkle path that reconstructs a given Merkle tree root. So in the zero knowledge circuit for the inclusion proof, for a semaphore proof, you need to essentially verify that you own a private key to a public key, which if you have the Merkle path for, you construct the Merkle tree root. So the Merkle tree root needs to be public in order to verify the proof, because that's the most important public input to that proof, to the circuit. So if we check how one of these bridge contracts work, essentially Optimism is a rollup. It's an optimistic rollup, and rollups have native bridges on Ethereum. Every single rollup posts every single call data of every single function of every single operation that happens on the L2 to Ethereum mainnet. In order to update the state of the rollup and in order to settle on Ethereum, to inherit Ethereum security. And the way that you update this function is by going through like a proof. You either do an optimistic proof where you have this like 7-day delay period where you're playing this fraud proof game, or on the ZK side, you just create a proof of the transition of the EVM, for example, on the L2. So like ZK EVMs, like ZK Sync or Polygon ZK VM and Scroll. So these rollups have native smart contracts on Ethereum that they use to settle those things and verify those proofs, and a bunch of other things like bridging state, for example. Bridging state is one of the most important parts, because in order to have state from Ethereum being useful within the rollup, let's say that you own a token on Ethereum and you want to bridge that token to Optimism, well, you need to have a bridge. And the bridge, essentially, the way it works is that you send tokens to a smart contract on L1. The smart contract on L1 will pick up that event, and the sequencer on the layer 2 side will issue a token that represents that token on the state of the rollup. And vice versa, right? If you withdraw from the rollup, it will burn the token on that chain, and it will unlock the token on the bridge, and you can withdraw it to any address on the L1. So this bridging mechanism, it's essentially a specific implementation of a general message passer. So this is essentially a way to pass messages from L1 to L2 and L2 to L1. And Optimism has a cross-domain messenger contract. And this cross-domain messenger, you can call a send message function that allows you to send any given payload to it. So in this case, we're just sending a root. So we're calling the World ID Identity Manager contract latest root function, and this will just return a uint56 for the latest root. We encode a function call for a given function called receive root. I'll show you that in a second, with the latest root as a payload for the parameter. And we call the cross-domain messenger with the cross-domain messenger send message function with this payload. So we first send it the address of the World ID contracts on Optimism, the message, which is which function we want to call with what payload, and the gas limit that we want to use in order to call that function on the L2 side. So as you may know, like there is a gas limit on Ethereum mainnet, and there's a gas limit also on Optimism. But in order to do a transaction on Optimism, you need to first purchase that gas on Ethereum mainnet before you can spend it on the L2. So this is just what that means. And once we do this call, we just emit an event. So on the Optimism side, there's an Optimism World ID contract. Let me just show you the interface that this is inheriting from the abstract. So this is inheriting from World ID Bridge. And World ID Bridge has a receive root method that we just saw. So the receive root method just takes in a new root. And if the root has not been seen before, then we just update the new root. One thing to note here is that you may think that everybody or anybody will be able to send in a new root, because There's no checks here. The way that that is worked around with is this cross-domain ownable 3 contract that makes it so that a contract on L2 is owned by a contract on L1, so that only the bridge is able to send routes, and the bridge can only send a route if it fetches it from the latest route on the world ID contracts. So this is sort of like a way to make sure that the route that is being sent to the L2 is the correct one, and not something that anybody can mess with and just create incorrect proofs and break world ID in turn. So once we have the world ID here, once we bridge the route, we update the route. And once the route is updated, anybody can create inclusion proofs against that route, right? We have, again, the verify proof endpoint or function on the contract, and anybody can verify proofs on Optimism now. So when I showed you the grants contracts before, these contracts are deployed on Optimism, and this check claim method is calling a world ID router on Optimism to verify this given proof. And the way that the state got to Optimism is through the world ID state bridge, which I showed just now. So this is sort of like an example of how you can bridge. And so anybody can write their own bridges, their bridge contracts. They can use either the native bridges. So for Polygon, for example, we used the FX root bridge. For Base or Optimism or any OP stack chain, really, you can use the Optimism's cross-domain messenger. For Scroll, you can use the Scroll messenger. For Arbitrum, there's this Arbitrum inbox contract you can use to send messages. Every single rollup has their own bridge contract and an implementation of a message passer. And there's also different bridging sort of infrastructure and protocols that have different security assumptions. There's protocols such as Succinct, which implement a ZK bridge that allows you to bridge state to different networks as long as they verify these proofs. I think it's called telepathy, if I'm not mistaken. There's other protocols such as Layer 0 or Connext and many other protocols. Wormhole, for example, if you want to bridge to Solana. There's many different protocols that anybody can integrate with to sort of propagate the state from world ID on a third mainnet to their own network so that they can create inclusion proofs on their target network. One thing to note is currently the only implementation of world ID is in Solidity for the EVM. So if you're bridging to a non-EVM network, you have to do your own implementation of world ID, which might not be as secure as the implementation on Ethereum mainnet or for the EVM, because the implementation that was done by us has been audited by Nethermind. So if somebody wants to build their own implementation, we strongly suggest them to audit their implementation and make those audit findings public, address them, etc., create bounties for them, all those sorts of things that are standard in smart contract security practices. So that was everything, or at least a really strong overview of everything that World ID does from an on-chain perspective. So if we go all the way back to the very beginning, how does everything work? So the user, when they first want to sort of prove their personhood, they download the World app. The World app is just a client that allows you to hold public-private keys, one for the smart contract wallet for the safe smart contract wallet, and the second one for World ID. Once you have a public key for World ID, you go to an orb. The orb verifies or creates an iris code and verifies that that iris code is unique. Once that it verifies that, it inserts the user's public key into the verified set of users, which is the Merkle tree, by sending a identity commitment of their public key, essentially, to the signup sequencer. The signup sequencer batches those identity commitments and creates a zero-knowledge proof using semaphore MTB, right? These circuits. Using semaphore MTB, once you have that proof, you submit that proof to the World ID contracts, to either delete identities or insert identities. For registration, it's insert identities or register identities. So once you call register identities, you update the root, and now the user is in the set of verified users. If the user wants to create a proof that they're a unique user, they can generate an inclusion proof or Merkle proof from the signup sequencer. And once the signup sequencer creates this Merkle proof, the user can create a zero-knowledge proof of insertion using semaphore RS, which is another repo I showed earlier. Let me pull it up really quickly. Right, using semaphore RS, they can create a proof. And then this proof gets sent to the world ID contracts, to the verify proof method. And you can, actually not that verify proof, there's a different verify proof at the end, this verify proof, which verifies the ZK inclusion proof, the semaphore proof. So that's essentially like a whole flow of how a user can go to an orb and get a world ID and then verify that inclusion proof on chain. Of course, I skipped the bridging part, but it's the same logic. You can insert the new root with that given identity commitment to the Ethereum contract, then you can bridge that root to Optimism, and you can verify the proof on Optimism instead. Or anywhere else where you have an implementation of World ID, a generic message passer that you can receive messages from Ethereum, and something that you can use to essentially serve inclusion proofs against it. So yeah, that's essentially it. There are some other components that are also used, for example, for the off-chain proof verification, right? So I mentioned that we have this thing called sign in with WorldCoin, which is a OAuth provider, like traditional authentication provider for Web2 services, where you can also verify and gatekeep services for SIB resistance for products that are not on-chain, just traditional web products. With like, for example, if you want to gatekeep an API, if you want to have a free tier for an API and you want to make sure that nobody's abusing it, well, you can gatekeep it with a world ID, and you can have a user session that you can know it's not DDoSing your API, and you can have maybe like higher limits for a free tier. Traditionally, services either require credit cards or solve like complex CAPTCHAs in order to make sure that it's partially at least not botted by some bot farm. Let's say like somebody using Puppeteer and trying to go through things by an automated process of some sort. The SDK is just a set of libraries that make it easy for developers to integrate these flows into their application. So if you're building an app with World ID on chain and you want to monitor, for example, that a given proof was successful on the chain, and you want to build a front end that reflects those things, you would use the World ID SDK to essentially monitor the chain that a proof was verified, and then you can allow and update the state on your front end application to reflect the state that just happened on chain, or the state transition that just happened on chain. So this is a holistic overview. We have a lot more resources on the blog posts that we have within the white paper. So if you go to whitepaper.worldcoin.org, you can go through lots of different things. You can go through like the motivation for why World ID even exists and why it is the way it is, why we use an orb as opposed to other methods. The technical implementation of the architecture I just walked you through, how the orb works, all the different components, how the biometric system works, how do you make sure that the person is actually unique by using iris codes, the WorldCoin protocol. This is essentially what I just walked you through the essentially use of World ID on chain, where you have a sign-up sequencer, the prover, semaphore MTB, semaphore RS, the SDK, the World ID contracts, the bridges. It walks you through all of that and different steps that you do. So if this video was left you hanging and you want to learn more, the World ID or the WorldCoin white paper is the resource to essentially learn more about all the different parts. Awesome. So I hope that was helpful. And if you have any questions, feel free to send me a message on Telegram or on Twitter. So on Telegram, I am DCBuild3R. So the link would be like t.me/DCBuild3R, or on X, I am x.com/DCBuild3R, DCBuilder Tarif. Right. So thanks for listening, and I hope to see you next time. Bye-bye.